Hi everyone. Today we're going to be talking about some examples of using Markov chain Monte Carlo to solve some specific data problems, and critically kind of how to set those up and how to determine when things are working or not, especially in the case of pymc. So what we're going to do is focus today's study on this pymc package. And again, we're doing that because it's kind of the less familiar approach to how we might be thinking about this. The MC package that we promoted in the last video is very good when you can write down the log probability function. It's low dimensionality data, and it kind of works and is fairly intuitive. Thus, it makes sense to kind of pay attention to the thing that's less intuitive here. So we're going to start out by just talking about how to characterize a distribution of data using the pymc package. We'll introduce the idea of mixture models, and then we'll do a slightly fancier regression model than the sort of the sort of linear regression that we've been focusing on all along. So the first thing to think about is characterizing the distribution. So this is a data set that you've seen before. This represents historical measurements of the speed of light using the method of aberration. And we know that the answer should be 299,792,458 or so somewhere around here is the correct value of this distribution of data that people were trying to measure for the actual speed of light in kilometers per second. And we'd like to use this to infer what the speed of light is from these observations. So we can construct a data model here. And let's use the framework of a graphical model, because that's how pymc would think about this. So we're going to sort of lay down two different approaches or two different parameters here, where we say that this distribution is going to be described as a normal distribution with a mean of C, like what we care about, and then a variance sigma squared. The variance is going to be described by this parameter sigma, and we're going to assume it's distributed as a half normal function, which is going to have its sort of below zero, it's going to have no probability, and then above zero, it's going to be 1,000 squared, so basically 1,000 kilometer per second width to that distribution. And that seems reasonable since we go from 299 to 301, so that's 2,000 kilometer per second full span. So this is half of that. Okay, that seems reasonable there. And then we'll assume that there's a 1,000 kilometer per second spread in the normal distribution for the speed of light. And that feeds into this collection of data. So the way it will work in pymc is to actually set up the same graphical model. We're going to get some measured data of the speed of light. They read in from a pandas data frame. We convert them to NumPy. It has some weird special character in it that I didn't clean out of the data file. Sorry for that. And then we have the creation of the model. So we instantiate a pymc model for this. And we just write down, we say, okay, the variance here is going to be the half normal. I guess it's not the variance, it's the standard deviation. It will be a half normal with a width of 1,000. The speed of light will be a normal distribution with a mean of around 300,000 kilometers per second, a width of 1,000 kilometers per second, which is all reasonable values given the data set that we're working with. And then we say the observation is going to be normally distributed with a mean of C, a width of whatever width we measured here. So remember, these are the prior distributions. We're going to use the data to infer the true values. And these are the observed values. And then we just sample. We use, here we're going to use 1,000 tuning steps, which will just basically be how long it takes to find the mean. So these are things that will get thrown away, and then we'll sample 1,000 times after that. And then this just tells me to use 4 cores on my computer because I like parallel processing, and that's cool. The resulting distribution, which we pull up with RViz and we ask it to show us the traces, it says, okay, here's the mean of the distribution and then the width here measured. And you can see these look like fairly good traces. We don't see a lot of separation. They're all bouncing around pretty effectively within a probability. So it should just kind of look noisy here. So far so good. But let's actually get down to what the actual measurements are. And one good way of doing that is to use this rviz package called summary, and we just pass it the trace variable, which was the result of the sampling function. So we sample it into this variable called trace, and it will spit out a value that looks like this. And it'll tell us the parameters C and var. It'll tell us the means over the distribution. So that's the expectation value of these two distributions. It'll tell us the standard deviations of those. So that's the widths of these. And then it will tell us the highest density interval. You can set the parameter here, but this sort of runs from the 3rd percentile to the 97th percentile by default. And it tells us kind of the credible ranges of these variables. Again, you can tune it. Then there's this Monte Carlo Markov chain standard error. Shows these means and values here. And then the effective sample size for basically how long effectively the chains were given value. So we gave it 1,000. There were a bunch of, there were sort of 4 walkers here, and so it says, okay, this is basically how many samples we're drawing. And critically, this tells us the R hat value. And so motivated from last time where I explained this was the chain-to-chain versus the intra-chain variance. And we see good value, 1.0. We don't want this to be much larger than 1.1. We don't want this to be larger than 1.1, indeed, or much larger than 1.01. So things are looking good. We've got a nice set of values here. So this would be quickly how we would pull these values out. I focus mine on my attention on the R hat, and then the credible ranges here, and then taking a look at the trace plot. So it looks like we got some good sampling going on. What we'll do next is we'll say, well, this is a little problematic, or it's not problematic, but if I look at this, it doesn't look fully normal. It looks a little skewed, right? There tends to be more values above the mode here than values below. So it looks like we have a little bit of a skewed distribution. And so I might actually say, well, a better data model for this would be a skew normal. And so we're going to bring up this distribution called a skew normal distribution, which has parameters C, sigma squared, and alpha. And I'm going to say, well, I'm going to model my collected data as that. I'm going to assume the same distributions for the normal, for the sigma and the C parameters. And I'm going to introduce a new parameter, alpha, which is representing the skewness. And I'm going to say it's positive, or it's a normal with a variance of 1, so it can be positive or negative. And the skew normal distribution has a PDF that looks like this, which is a normal function. That's this component here. So, 1 over the normalization term, e to the minus x squared, x squared minus mean over the standard deviation squared. And then there's this extra function, which is an error function, or ERF, of alpha times basically the argument to this function, x minus mean over the width here. And the error function is just the integral of the Gaussian up to whatever the argument is here. So this essentially is a nice, sort of smooth function. It looks like a logistic function or something. But this product here ends up giving me a nice skew distribution. Here's some examples of the skew normal. This gives me a parameter. If alpha is 0, this distribution is just a Gaussian distribution. It's exactly a regular Gaussian. If I set alpha equal to 4, you'll see that it has a positive skew tail running out in this direction. And if alpha is equal to -2, it skews to the negative side. So it does a nice job of being roughly normal while also being capturing a little bit of the skew. And so what I set that up for is the exact same thing, where I have the same variance and mean to this value. And then I say, okay, well, I'm going to introduce this skew parameter with mu equals 0 and sigma equals 1. And I feed these three priors into my observed data, which is a skew normal, with a observed set of data here. And then I fire off an MCMC run. So I have this second model coming together. And I get that there is indeed significant positive skew to the data when I get the trace. It's coming in here about 2.5 as the skew parameter. You can see maybe there's some excursions here that are, it's not fully, bouncing around and looking like pure noise. We're getting a little bit of interaction between these parameters. And we get a significantly lower value for the mean value here. So this is the mean for the speed of light is coming in a little low, in fact. And then here's the variance of the distribution. And then I can pull this out where I figure out what the skew, the mean, and the variance for these measurements are, including the confidence intervals. You can see we're still not quite spanning the true values of the speed of light. And my R hat values are a little larger than last time. And I think that reflects these like excursions up here. So it shows that we're not in the full danger zone of larger than 1.1, but it looks like the chains haven't quite settled down here. But what's kind of neat about all of this is I have two different data models, and what we're going to do is we want to compare them. And previously we've said, well, we can use the AIC or the BIC to do those. But what we're going to do is we're going to focus on the toolkit that's embedded in pymc, which is suitable for Markov chain Monte Carlo sampling, because the ASA and BIC assume that you have the maximum a posteriori probability of the values that you're actually comparing. And the MCMC, you would actually have to sort of infer where that is and kind of take you'd maximize the probability, and instead we're dealing with a bunch of draws from the probability distribution function. And the way they use that is this method called, or the way we want to take advantage of that is to use this leave one out cross-validation approach. So you'll often see this described as a LU here. And you compare these two models. You basically have to say, okay, for using these two models, why don't we, as context, compute the log likelihoods, because it's not kind of intrinsically brought along with the calculation of MCMC. So we need to know what the log likelihoods of every sample is. So this will calculate those. And then we just tell the RViz package to compare the normal and the skew normal, which have these corresponding trace vectors. So you pass this dictionary there and use this leave one out information criterion, and it spits out the result here. And the neat thing about this is if you give it a nice list of models, it just tells you which one is better. And the thing that we look at is for this leave one out cross-validation method, you look for the thing that's kind of closer to 0. So this ELPD is higher for the skew normal relative to the normal, and it tells you basically significantly so. The probabilistic weight that the skew normal is better than the normal is significant. So the weight is a lot larger. It has this nice warning value to tell you, okay, is there any problems with my measurement? Here it says, no, everything is looking good. So everything here indicates that the skew model is actually a better data representation than the normal. So this is using a version of an information criterion that is appropriate for our Markov chain Monte Carlo sampling and relatively small numbers of data. For larger numbers of data, you change this information criteria to the WAIC, which is often shorthanded to the widely applicable information criterion, which does kind of a similar approach, approximates the probability functions from the traces. So this gives you a nice way of actually comparing these different models here. For our next example, we kind of want to look at a mixture model. So this gives us an important kind of toolkit here for exploring some data. So we've faked up some data here that's shown here. This is a data set that includes 50 samples drawn from a normal distribution centered at 0 with a standard deviation of 0.5. 80 data are drawn from one centered out here at 3 with a standard deviation of 2, and then 50 that are drawn from a sample centered at -2 with a variance of 1. So that gives us, a data set that looks like this. We'd like to ideally infer the properties of these 3 normal distributions. So those data are kind of shown here as to where we're getting these 3 samples from. And you can see that it's not exactly lined up with this nice kind of chunky data distribution, but we nonetheless would like to infer these 3 properties. And graphically, we describe this by saying, well, we have 3 models here, so we say there's a collection of 3 models that each have their own variance, their mean, and we've picked a mean that kind of has a standard deviation of 5. So that means the means of the distribution can kind of go end to end of the observed data. Kind of a standard, weak prior on the standard deviation. And then we also have a weight function, W. And we say that there's these weights kind of represent how much each probability distribution function contributes to the whole PDF. And that is going to have a prior on it called a Dirichlet distribution. More on that in the next slide. And so we're going to assume that there's this 3 collections, and this fully feeds into a normal mixture model, which is basically a sum of 3 normal data or normal distributions with a vector of means, standard deviations, and weights. And there's going to be 180 data that are giving us this constraints on these 3 parameters. So a Dirichlet distribution is formally a multivariate generalization of the beta distribution, which we introduced like couple, 4 lectures ago here. And formally what that is has a normalization factor, and it's a product of the values x raised to the alpha minus 1. So for a high dimensional vector, you just multiply up the components raised to each of these powers. This normalization function is the multivariate beta function, which is a product of gamma functions over the parameters alpha. So you take the product of the gamma applied to h alpha, and then normalize that by the gamma function of the sum of the alphas. And the key thing here is that the Dirichlet distribution constrains the x's to be within the 0-1 interval, and they have to sum to 1. And this is the key thing, is that it is allowing us to say that there's some vector of in this space, in basically this kind of not even octant, the section of Rn, which is between 0 and 1 on every component, and then the sum of each of those adds to 1. That makes it perfect for a weight vector. Absolutely great, because the weights really should sum to 1. So we use this all the time. And we've also picked alpha I equal to 1. If you go back to the model, it's 1, 1, 1 for a three-dimensional model. And that just means that this is alpha 1 minus 1 is 0. So this is just the product of a bunch of 1s here. So it's a flat distribution, so you're not tilting it towards one dimension or the other. So it's just a very convenient way of saying, well, there's going to be these weights, but they are constrained so that the sum of the three weights is equal to 1. So that's perfect for a sampling distribution, and the Dirichlet distribution has some nice properties that we can sample from. So it's well established, and it's a really common piece of our toolkit. So then our normal mixture starts to look like this. So we say, I want a three-dimensional model. I'm going to say that there's going to be 3 components in it. And then I say they have a mean where it's a vector mu. I'm going to pick my center. I said 0, 5 previously. Here I just went empirical. I said, give me the mean, give me the width of the observed data as the mu and the sigma. And then I'm going to say it has a shape, which is how many dimensions it is, of n comps. So three-dimensional shape. And then I have to do something kind of clever where I say I need this to have a ordering constraint. So this is pymc distributions transformed ordered. What this does is it keeps the 3 mu's ordered with respect to each other and kind of keeps track of which ones they are, because as we're walking around, the mu's might switch order. And what this does, it says, okay, I want to always keep track that 1 is always the lowest value, then there's the middle one, then there's the top one. So it keeps the walkers to be constrained to be ordered with respect to each other, which makes it possible to sort of have them lock in and sample a specific case. So this ordering constraint is brought in by this transform command. For the sigma, I assume it's inverse gamma, alpha of 2, beta of 1, 3 dimensions again, so n comps. And then the weights will be this Dirichlet distribution, where A is the alpha parameters there, and it's just going to be some 1s of length n comps. And then shape will also be 3 dimensions. So this just basically constrains the weights to be 0. And then pymc provides us with a normal mixture. There's also a more general class called mixture if you don't have normal distributions. But normal mixture allows us to pass in a vector of weights, vector of means, a vector of sigmas, and then the observed n-dimensional data. And then we just go ahead and sample it. So for this case, we do a couple things. First, we're going to tune for 4000. We're going to use 4 cores. That's all fantastic. We're going to pass this idata quargs to say, go ahead and calculate the log likelihood for all these. So all this does is it saves having to calculate the log likelihood in a later step. So you can just do that. And then we also, with this ordering constraint, we do need to kind of pass it an ordered vector of where to start. So I say start the means at -0, 1, and 1. And go for it. And then it roars off and goes and it finds the means. It says there's 1 around -2, 1 around 0, and 1 around 3, which is indeed really close to what we have. And you can see that these traces sort of look nice and well separated here. Occasionally you get a little bit of jiggling around and maybe some interchange between the means, but the ordering constraint keeps these well separated. You can see the different variances measured, and then the weights here. And you see that this one has a larger weight than the other two. That makes sense. The value up here at 3 had more data in it, and so it has a larger weight in my final sample. If I don't pass the ordering, you get a similar looking function, but you'll notice that the colors are swapping around. So if I don't put that ordered constraint in, you start to see the walkers, like you can see that there is a well-constrained value at 0 here, measured just like this one, easily measured same. So you are seeing the parameter at 0, but the problem is that the walkers are sort of bouncing around, so you don't get a nice clean 3 sets of independent measures. They just swap around. You can see 3 components here, but the different components are switching. So you need that ordered constraint. We can take a look at the summary here, and you sort of see the mean values for the 3 means, the 3 widths, and their relative weights all are consistent with roughly what we put in. Certainly it's spanned within the HDI, and you get a nice R hat values. Maybe we need to run a little longer to get the chains to settle in. So that's all. Pretty good. So we did our mixture model, but it doesn't seem completely finished because we stuck in 3 components and we knew there were 3 components. If we're doing this analysis without any insight, we would probably want to do a 2-component fit. So I've written the code back here where all I have to do is change the number of components and then the name of the model, and it should, and then the init values, and it will go through and it will check for a 2-component. And you see that here. And so it finds one model here that kind of spans the 2 negative components, and then another one way up here, which spans the positive outliers. And you can see the relative mixtures and the relative weights of these 2. And this one's nice and symmetric because there's only 2 components. If one is high, the other has to be low. So that gives us, these results here. We can also run for 4 components, where you get the 3 original ones and then maybe an extra thing hanging around here at the center, the 3 relative weights and their respective variances. And of course, we set all of this up, and we've gone ahead and we've calculated the log probability, because we can take these 3 models and feed them straight into this model comparison using leave one out cross-validation, and we get this nice representation of these 3, and it ranks them with respect to each other. And it tells you that the normal mixture with 3 components is the best representation of the data, and then 4 and 2 are also pretty good. You'll notice that the competition is still pretty good. So normal mixture 4 isn't super ruled out. 3 is preferred, but 4 is also a possibility here. So you can start to see, and then normal mixture 2 is definitely small compared to the other 2 cases. So that's fantastic. We actually can use Bayesian analysis to prefer the 3 components, which is indeed what the model contained. So great. I have a large success using this normal mixture model. And so that gives us a framework for kind of addressing all of these combined data models. We can use like multiple different types of distributions when we take this approach. The final thing I want to talk about is a regression model. And in this case, we're going to consider the regression model with uncertainties in both dimensions. I call this the hardest problem in statistics. And I'm going to solve this under the very specific case where we want to predict y as a function of x, i.e. there's a very clear dependent variable. So we want to figure out the response of y as a function of x. And I've said that this is statistically different from saying, is there a relationship between x and y, where you don't know which one is the dependent and independent variable. This case, I'm going to take advantage of saying x is the independent variable. So the way it's going to work here is we're going to set up this model where we have m and b, and I'm going to use a tool that's just called a flat prior, which is essentially, it's an improper prior, so m and b could be anything. And that's something that's nice and implemented in pymc. And then I'm going to assume that there are some true x variables. And the neat thing about the true x variables is I know that they are normally distributed around the observed data with a covariance matrix that's specified by the data here. then I'm going to assume that these three generate a true y value that I then have a normal distribution where I am observing the y with some fixed uncertainties in y. And this contracts down to a nice, fairly simple model. So I can set up my pymc model here, and I say that m and b are flat. There's no parameters on a flat distribution. They're largely unknown. And then I say my true x is a multivariate normal called true x, where my mean are the observed x values, and then my covariance matrix are my error values squared. And what this does is it creates a tensor where these values are on the diagonal. And then I say that it's going to have a shape that is the dimensionality of x. So this is fine. I have 16 data. What I'm doing is I'm creating a 16-dimensional Gaussian distribution for my x values. And I know that they are, so we're kind of inverting the role, and we're saying, okay, the true x are distributed around the observed data with my uncertainties. So if I believe my uncertainties, this is fantastic. My true y value is then a deterministic variable that is set by my slope times the true x plus the uncertainty. So these three are random variables here. And then I observe my y data with a mean of the true y, and my width is my known uncertainties, and I'm observing their y values. And then I can say, okay, go forth and sample that for my distribution, and I get some results that look like this. I get a well-behaved slope and intercept that are consistent with what I'm expecting. And the neat thing is that I actually have conditional posteriors on every individual datum, because I have modeled every one of the points. I can sort of figure out what my true x values are. These are kind of boring. These are just the uncertainties of this. They're sort of the characteristic widths. But you can see that the fit, saying that these are all coming from a single fit here is actually constrained. You can see some structure in some of these that basically says, well, because we know these come from a fit, we actually prefer values that are different from the observed values plus their errors. We actually are getting some information on where the x's and the y values are independently. So you can see that low datum here, we actually have little constraints on it. And so you sort of see the structure of the bands here. So this gives us a way of treating that particular problem. Now, this is not the only way to formulate the regression problem. I'm not going to drag you through all of them, but this was the specific case where we knew that y was the dependent variable and x was the independent variable, and we wanted to predict y from x. If we don't know which one it is, then we have to kind of create a two-dimensional normal distribution and sort of have my x's and y's float around in there, and that's a different problem. But this is one where we could just sort of figure out and sort of model where the true x's are, figure out where the true y's are, and then say we're actually observing those y's. So we're able to separate the x and y values very cleanly. All right. So this brings us to the end of the examples. I've sort of summed up what I wanted to present. I gave you a few examples in pymc, and then gave you a couple of really important toolkits here. I think the Dirichlet is the most important because it's an essential tool for mixture models, and when we're kind of combining up and figuring out what the combination of multiple data distributions are. So that should give you a toehold into like starting to read through and interpret what's happening in the pymc package, which is really powerful. It's not to exclude MC, it's just this is, I think, the case where it is less obvious how this tool works if you've been thinking about optimization for a while. Anyways, talk to you later. Hope you enjoy exploring data probabilistically.